Okay, so let's look at memory because memory is a very important part of what you do in really embedded processing. Now, there's different kinds of memory. there, some people say they're between RAM and ROM difference, but really the more accurate terms are volatile memory versus non-volatile memory. So RAM stands for random access memory is often used to refer to volatile memory, but even the term random access memory is a misnomer in that most memory, even ROM, is random access. That is, you can randomly pick a location. So that is by randomly, that means you can give it any address within its space, and then be able to read it out or write it. Okay, that's what access means. Access means reading and writing. If it's reading only, then that doesn't quite mean access. If you cannot write to it, right? Access means reading, writing. So that's what RAM means. Random means you provide an address. Any address you come up, it will follow and then fetch that location or write to that location. So that's what RAM means. But really, by RAM, people really assume that it's volatile. What does volatile mean? That means normally you have to provide power to it. If you cut the power, its content is lost forever. You cannot get it back. Okay, so that's what happens if you're writing your word processor. You forgot to save your file. Somebody pulls your plug. And you're gonna hit them. You lose your work. Disk is not volatile because if you save it, you cut the power. Okay. Oh, good. I saved it right before they pull the cord. Okay. So disk is not volatile. Now, so random access is emphasized because you want to contrast it against something like structured access. So what's structured access? So there's components that are like stack or queue. Stack is last in, first out. Queue is first in, first out, right? So with a stack or a queue, you could actually find a little chip that's a stack chip or a queue chip. With something like that, you don't provide an address because you cannot randomly say, I want the second to the last element that you just put in. No, sorry, that doesn't happen with a stack or a queue. With a stack, you only get the last item you put in or wrote. With a queue, you get the oldest element that you put in, right? So that means you have to give an address explicitly when you do access to a volatile or RAM. Now, non-volatile memory, which people call ROM, read-only memory. Again, ROM is a misnomer because most ROM can be written to. So strictly speaking, they're not read-only. But what they really mean is that the content is retained even after you cut the power. Okay? So, and randomly addressable in that you can say, I want location 32, and then it'll give you the data at location 32, or you want to write to that location. So again, you give the explicit address to name that location for reading and writing. Now, RAM. RAM can be divided into static RAM and dynamic RAM. And so I don't know if you know the difference. I guess computer science people may or may not know the difference, but this is pretty important difference in terms of hardware. And so the SRAM or static RAM is what's used in most embedded systems as built-in memory or on-chip memory. Whereas DRAM or dynamic RAM is what you find in PC. So your PC, if you want to do memory upgrade, you get one module to plug in or a couple modules. That tends to be DRAM or dynamic RAM. Now SRAM is more expensive, but easier to work with, lower power and so forth. DRAM, on the other hand, has higher capacity, but just more complex. It's also cheaper. So we were talking about the difference between SRAM and DRAM. So I'll just give you a brief version of the difference. So this is what an SRAM cell looks like. It takes 6 transistors to store 1 bit. Where are the 6 transistors? Well, there's one that looks like this symbol. So it looks like a 3-terminal device, right? And then it's like a little pulse and then the inverted T, right? Okay. So the T part, that's your on-off control. So it says connect or disconnect the 2 sides. Okay. So that's a switch, kind of like a light switch, connect or disconnect. Okay. So depending on if there's a voltage or not. Now, so there are 2. One is for the bit and one is for bit bar. So that means it's the complement. By complement, I mean, if it's a 0, then bit bar is a 1. If bit is a 1, bit bar is a 0. Okay. And those are the 2 switches. But in addition, but what's actually storing the value is those 2 triangles with the bubble on the tip. So remember what that symbol is? That's called an inverter, right? You all had digital logic, right? An inverter takes a 0, makes a 1, or takes a 1, makes a 0. And these are what's called cross-coupled inverters. So that is the output of one goes to the input of the other. And so this is both basically mutually reinforcing because it has 2 steady states, right? So if one side is a 0, the other side will be a 1, and they will reinforce each other, right? Does that make sense? Right? Because one is driving the opposite value feeds back to itself, right? And then you have one steady state that's a 0 on the left and 1 on the right. But if you have a stronger signal to change it to the other side, then it can flip, right? And it could be a 1 on the left and 0 on the right. And then they will reinforce each other. So it takes some power to overcome its steady state. But once it's overcome, then it remains in that steady state. So it has 2 possible steady states. It will not consume very much power when its value is not changing because there's really no direct path for current dissipation. There's probably a little leakage, but it's retaining the steady value, mutually reinforcing. So typical representation or implementation of SRAM is 6 transistors per bit because an inverter has, right, it uses 2 transistors, right? You may have taken VLSI courses. So that's 2 plus 2, and then the 2 switches, those are 6. Now, some people can optimize the design of SRAM cell down to maybe 5 bits, but still, that's costly. Now, on the other hand, you have dynamic RAM or DRAM that uses just 1 transistor per bit. And this is what the schematic looks like. You have the data line and then the read and write line. And that's basically just a switch. And then the symbol on the right, that's called a capacitor. And the capacitor really doesn't cost much. It's just metal and with respect to ground. And you know what a capacitor does? Is it holds charge, right? And if there is no path for the charge to flow, then it keeps its value. Of course, there's a little leakage. And so slowly, the capacitor will lose its value. But it holds long enough so that for all practical purposes, it's retaining its value, okay? So to read or write, basically you open that, you close the switch, that means you connect the switch, you let the value flow in or out. Once the bit part or storage part has the value you want, you then disconnect the switch. Then it traps the charge or traps no charge, right? And that's how it remembers things. And then next time you want to read it, or then you connect the switch again, then the value flows out. But then reading is destructive because once the value flows out, there's no more value inside for the capacitor, right? So that means you have to replenish it. So you have to. So a DRAM access is more complex because of this, right? Because then, when you read it, you suck out the charge, but then you say, oh, I just lost the value. I have to put it back. So it needs to then make a copy, and then of course using something like SRAM. Then it replenishes the charge back in so that it can still remember the value. So reading is destructive. Now, in addition to refreshing upon reading, periodically you also need to refresh because all DRAM cells will leak charge, right? So keep drop until it hits some critical threshold. Because that threshold, beyond that, you cannot distinguish between a 0 and 1. So before it drops below that threshold, you better copy it out and then put stronger charge back in so that it can still remember the old value. Okay, so as you can see, it's more complex. But then that refreshing logic can be shared for all the DRAM cells. So that's a price to pay. Because it's much fewer transistors per bit, you can have much higher density. That's why most computers, general purpose ones that is, use DRAM as opposed to SRAM, just for higher capacity. But you have to then do the refreshing. And then, of course, refreshing means you keep consuming power. So DRAM will cost more power. And that's why for embedded systems, we tend not to use DRAM as much unless